Good afternoon, ladies and gentlemen. Welcome back to this second E-Symposium on Sustainable Transformations on Plant-Based Oil and Waste towards Circular Economy, Health and Well-being 2022. So we are now in the sections of Waste to Wealth, okay? And I am Lee from Divisions of Green and Sustainable Chemistry, Institute of Kimia, Malaysia, and I will be chair for these sessions. So agenda reminder to all our speakers to complete the presentations within the designated time to avoid any delay in closing these sessions. And now we have our first keynote speaker, Dr. Pushpa Malajanatanand from School of Science, Monash University, Malaysia. Dr. Pushpa is a senior lecturer and deputy director of Monash Industry, Palm Oil Education and Research Depot at Monash University, Malaysia. She received her PhD in Applied Polymer Chemistry from Monash University, Australia in 2010, and her bachelor's and master degree in Polymer Chemistry and Pure Chemistry, respectively, from University Putra, Malaysia in 1996 and 1999, respectively. As the Deputy Directors of MIPO, she served as a platform of contact point for university, industry, government, corporations to improve the competitiveness and sustainability of the palm oil industry in the country. She also actively participates as an associate member of the Malaysian Institute of Chemistry in organizing national and international conferences. Besides, she is the editor of a book on nanomedicines. Her research aims to develop biodegradable polymers for compostable plastics and control the release of active agents for various industry applications. Okay, so I am honored to invite Dr. Pushpa to share on the topic of oil palm biomass exploitations for medical use. So the stage is yours, Dr. Pushpa.
Yeah, thank you. I'm Dr. Pushpa from School of Science, Monash University, Malaysia. I'm going to talk about oil palm biomass exploitation for medical use. So I have taken up empty fruit bunch as the biomass from the oil palm industry and exploit it to make materials that can be used in medical area. So here is my email address, and I have a research group website. So you may also tap into that website to look into my research work, my research students, awards given, grants, and so on. So all the informations are there in that website. Yeah. So a little bit of introduction to Monash University, Malaysia. So it is situated at Bandar San Way, 25 kilometers away from Kuala Lumpur, and established in 1998. And it was at the time first foreign university campus in Malaysia. So it is also a research-intensive Australian university ranked among the 100 universities in the world by the Times Higher Education World University Rankings. Also a member of Australian's prestigious group of 8. So these are the universities that involve in intensive research works. And Monash University is ranked 58 in the QS 2022 World University Rankings. And we have about 9,200 students from 76 countries, makes it a culturally rich environment. So we have many students from different countries, speaks different languages. And the students are taught by highly qualified academic staff from across the world, and the same rigorous standards are applied at the campus as at other Monash campuses. Yeah, so it's the same standard as other campuses in Australia, in other parts of the branch Monash campuses. Now, I think we are familiar with the Sustainable Development Goals. So this goals is attempt to reduce the carbon footprint, or if possible, maintain the carbon footprint in the environment. So my research usually adheres to this UN's Sustainable Development Goals. So looking through all my research work, I have classified that it adheres to 4 out of the 17 goals, which are the SDG 2, Zero Hunger, SDG 6, clean water and sanitation, SDG 12, responsible consumption and production, and SDG 15, life on land. So you can see the 17 goals here. So my research fits into 4 out of the 17, and possible I'm trying to increase the numbers to fit into these goals. Yeah. So the oil palm industry is the primary producer of biomass in Malaysia. So the oil palm industry biomass outputs are, as we are familiar with, oil palm frond, oil palm trunk, which is the major contribution to the biomass, and we have palm press fiber, empty fruit bunches, palm kernel cake, and palm effluents, and decanter cake. So these are the biomasses. The part that I'm interested is the empty fruit bunch, yeah. So which actually gives out about 14% of the biomass. So this EFB can generate as a byproduct from the palm oil production. So if it is thrown somewhere in the environment, so that poses a threat to the environment. So we are trying to convert this EFB into a useful or value-added product that can be commercialized. So as in the lab, as we've done, the EFB that we have got, it is very highly fibrous, and it contains 34% of cellulose. So this is what we have come up in the lab. Now, using that cellulose that we have obtained, yeah, so this is overview of my research work in the using the biomass. So first of all, you look at the picture here is the fresh fruit bunch. So this is what you get from the plantation area, and after taken out the fruits, so this is how the empty fruit bunch looks like. So it's very, very fibrous, very hard, and we really need to use a ball mill to grind this empty fruit bunch into a ground empty fruit bunch here. Yeah, so after we have ground this into this form, so we convert that into cellulose by delignification process, and we get this white fibrous material as a cellulose. Yeah, so this cellulose we convert into 2 products, yeah, for further usage in the research work. Yeah, so because cellulose is insoluble in water, so we need to make it that is soluble in some kind of solvent. So what we did was we converted into carboxymethyl cellulose. Yeah, so this is adding in carboxymethyl group into cellulose structure. So whereby it gives CMC, which is dissolved in water. So then further we can use that into making materials. So what I have done here is I have prepared nanostructured lipid carrier for drug delivery using the carboxymethyl cellulose from the empty fruit bunch. And further from the cellulose, we have extracted nanocrystalline cellulose, so removing the amorphous part of the cellulose, leaving behind the hard part of the cellulose, which we call it as nanocrystalline cellulose. And this nanocrystalline cellulose has been incorporated to form nanofibers and a membrane. So this nanofiber that incorporated with NCC is for the biomaterial, and the membrane here incorporating NCC. This was by using the aluminum chloride by spraying method to produce electroactive material. So this has been presented. So this work has been presented by Mr. Kwong this morning. So you have seen, so this is how the film looks like, yeah. So he has characterized the film and presented just now, yeah. So today I'm going to present about this nanofiber here, the Electrospin nanofiber and the nanostructured lipid carrier. Now here, the preparation of the carboxymethyl oil palm empty fruit bunch cellulose. So basically this you have seen up to this part here. And from this cellulose, we convert that into CMC. So how do we do the conversion? So this is the cellulose structure. So this is the white hoodie material. So it contains hydroxyl groups here. And these hydroxyl groups will be substituted by the monochloric acid. Yeah. So how do we do that? We use aqueous sodium hydroxide to swell the cellulose, and then later adding in sodium monochloride chloride acid. So that will actually substitute these hydroxyl groups here. Yeah, so the maximum substitution could occur is 3. So usually we will get from 1 to 1.5. Yeah, so the maximum can go is 3. So that is the process to form the CMC. So CMC means over here, since it is produced from the empty fruit bunch, we call it as a carboxymethyl oil palm empty fruit bunch cellulose. Yeah, so it's actually the structure is carboxymethyl cellulose. So we name according from the source of it. Now the preparation of nanocrystalline cellulose from empty fruit bunch. So we have seen up to the cellulose here, and removing the amorphous part of the cellulose is done by hydrolyzing it with 64% of sulfuric acid at 45 degrees Celsius for 45 minutes. Yeah, so you get the nanocrystalline cellulose here. So this is in the solution. So when we want to get it in terms of mass, so we centrifuge it and then remove the solution, and we get the pellet and dry it to get the mass of the NCC. Yeah. So these are the two products that I prepare from the empty fruit bunch, which I will use for my further work. So this is the first work. So I've mentioned earlier, I will be presenting 2 parts of my research work. So one part is here, which I use the nanocrystalline cellulose to form the nanofiber. So the matrix will be polycaprolactin with the lignin attached to the aminated PEG. Yeah? So this matrix we reinforce with the NCC that we have prepared in order to prepare a biocompatible and antioxidant wound dressing. Now this NCC that we have prepared, when we run the charge on it, so the average zeta potential for this NCC was -65, which is very negative. And this could be due to the sulfuric molecules during the hydrolysis process. Yeah, so the negative charge actually led to stabilization due to the repulsion, repulsion process, which prevent the aggregation of the particles. Now, this NCC that we have got, we measured the diameter. So the average diameter of it is 1.96 micrometer with the maximum distribution of 1.2 micrometer. So if you look at it, it's quite big. This could be maybe due to the aggregation that we have measured it, with couple of NCC intact together. So we need to do further research. So what we did was we did a Afm imaging. So we found there's a slight agglomeration of NCC. So some are in bundles, some are dispersed crystallites, and some are in the individual crystals, ranging from 50 nanometer of diameter. Okay, so these are the nanocrystalline, and you can see they are still in the close intact. So they're in a group. They are not in a single crystals. So we have used this negatively charged NCC in the electrospinning dispersion. So that actually aids this process, where we use lignin with the aminated PEG matrix. So it forms the NCC will be placed in the matrix. And further characterization of the NCC, we did Afm imaging. So it shows that the NCC is rod-like structure and has got the average of 15.9 nanometer. So you can see this is much smaller than what we have got earlier. So this could be because we have diluted the sample for AFM, and we have agitated using homogenizer, and later we have done this analysis. So you can see it's much scattered and really showing the nanocrystals, single units there. Yeah. So that gives you the real diameter of the NCC that we have prepared. In the blank PECl, polycaprolactone and lignin, okay, so it shows that nanofibers are 470 nanometer. Yeah, the diameter is 470 nanometer. However, when we incorporate 5 and 15% of NCC, it is ranging to 330 to 380 nanometer, showing that there is a decrease in the diameter. Yeah, so placing the NCC actually decreases the diameter in the electrospun material. Yeah, whereas the material that added with 10% of NCC, it shows much higher. Yeah, so could be due to the arrangement of the 10% of NCC is different, okay, in the electrospun material. Yeah, so here it is showing how the electrospun looks like. So first of all, to form this electrospun is not so easy. We need to optimize the conditions in the electrospinning machine in order to get this electrospun, and the combination of the polycaprolactone and lignin has to be also optimized in order to get beadless spuns, yeah, nanofibers like this, right? So you can see a little bit of beads kind thing forms. So when you see so many beads around, then it is not a good electrospun, yeah? So we need to optimize it. Now, looking at the mechanical properties after loading the NCC, okay, so we found that the membrane with the NCC actually, the mechanical properties decreases from 2 to 2.5 times compared to the blank without the NCC. Okay, so the factors could be the disruption by the NCC or the aggregation of NCC is not suitable to form a very good mechanical strength materials, right? And the one that the lowest elongation at break for 10% NCC, yeah, so this one here, this could be because of it has introduced a bit of plastic properties in there. Okay, so that could have lead to the lower elongation at break. Yeah. Now we have done some cytotoxicity study, and so in order to prepare a biomaterial for wound dressing, so the biocompatibility is very crucial feature. So we need to study on that. So here we have got electrospun, which for cytotoxicity study, we need to make a leach liquor. Yeah, so we put it in the nutrient and we let it there for 24 hours, 48 hours, or 72 hours. And then we take out the leach liquor and then we test it with the cells that we are working on. So here is the normal human dermal fibroblast cell that we have used here. So the electrospun that without NCC actually showed slight cytotoxicity at 24 hours, which is about 67%. But after the 24 hours, the cell viability has increased to 128%, yeah, after 72 hours. Now, the one with the NCC, okay, so this cell viability is about 86 to 111% over 72 hours. So you can see from here, the green one is with 15% NCC, the black one is without NCC. Yeah. Now, here we assume that leachable compound of the nanofiber promotes the metabolism of the cells that enhance their proliferation. Yeah. That gives you the higher cell viability after 72 hours. So this is demonstrating a promising potential material for biocompatible wound dressing with antioxidant property. Yeah. Now, the second part of the research that I would like to talk about is the preparing of a lycopene-loaded nanostructured lipid carrier from the carboxymethyl all palm empty fruit bunch that we have prepared from the empty fruit bunch for tropical administration. Now this, just to recall, if you have forgot, I have shown this just now. So this is the CMC that we have prepared. So we're going to use that. Now, preparation of the nanostructured lipid carrier. So we have got the lipid phase, and then we got the aqueous phase. So putting together carnauba wax, palm oil, and lycopene powder. So here, actually, what we are trying to do is that we are trying to entrap this lycopene, which is insoluble in water. So now we're trying to entrap it in the lipid phase. And later we will study the release of the lycopene. Now, putting lycopene in there at 75 to 80 degrees for 10 minutes. And on the other side, the aqueous phase will be between 80 with water. And then add them together to form the homogeneous nano emulsions. And later, we will add in the CMC solution, which is heated up to 60 degrees Celsius. Yeah. Now, once that have done, so what you get is the CMC should be at the outer layer, and the wax is in the middle, holding up this lycopene. So it entraps the lycopene in there. All right, so we have got this lycopene-loaded NLC dispersion. So we have got 3 formulations that we have made, and that can be used for applying as a topical drug delivery substance. Yeah. Now, why we want to prepare nanostructured lipid carrier is that it provides better drug entrapment and the release property, and the drug expulsion during the storage is minimized, okay, because it's entrapped in the middle, yeah, in the lipid, and it enhances chemical stability of entrapped lycopene compared to the free lycopene. Now, the surface morphology study of the CMC that we have prepared from the empty fruit bunch. So the first one is cellulose, and what we have got here is with the sodium hydroxide treatment and without the sodium hydroxide treatment. Yeah. So here this one is with the sodium hydroxide treatment, and the second one is without sodium hydroxide treatment. Yeah, so there's a little bit of swollen state of this cellulose. And if you look at the surface of the cellulose that without sodium hydroxide treatment, yeah, sodium hydroxide treatment, we call it as mesmerization treatment, that shows more dense and wrinkle due to the surface. Wax layer has been removed. Yeah. So now the CMC here, so it looks very smooth, compact and dense, indicating a compact CMC. We can get a better picture of this CMC. Yeah. So we are trying on that. So this is what we have got for now. Now, the preparation of the CMC and the NLC, and looking at some of their properties. Yeah. So the first table 2 here is that properties of the CMC that we have prepared. So degree of substitution. So we prepared in triplicate, and now we have got the average is 1.27. So the degree of substitution is 1.27. As I told you just now, the max that you can get is 3. Yeah? So we have got 1.27. And the moisture content is about 15%. So it's quite water absorbance property. So you leave it in the room temperature, it can absorb moisture. Yeah? The pH is quite neutral. All right. And then the solubility is about 97%. To 98%, yeah. So most of the CMC is can be solubilized in water, and this is the content of the CMC. Now, the NLC with the CMC formulation. So here we have done a few formulations to obtain the stable NLC. So the first part is with water twin with the lipid. We have found the properties here. The average particle size, zeta potential is the charges on the polymer, and the entrapment efficiency. So after adding in the drug, which is lycopene in this case. Now the W is for water, T is for twin, and this is the first formulation. So the next set will be with the CMC here, yeah. And we have increased from 2 to 3% of CMC, and then later NLC with the lycopene. So we have added 5%, 10%, and 15% of lycopene. And you can see the average size of particles that we have chosen as a bit away, yeah. So it's supposed to be at 32.7 here. So NLC1, okay, so that was the best formulation that we have got for 95% of lycopene entrapment, yeah. Now, the first step to prepare this NLC is using the palm oil and the carnauba wax. So using them together to provide a better storage stability. So this will reduce the crystallinity of the lipid part when you're adding in the oil, okay, to make it suitable, ideal composition. So it's very important to optimize this first. So the melting transition of the two different crystalline form of the palm oil and carnauba wax were represented by two peaks. So you will see if they are separated, actually you will see them as two peaks. Yeah, you will see them as two peaks. So with various combination, we have found the one that with yellow color, which is 5:3. Yeah. So the first part is the wax, and then the second one is oil. Yeah. So it's 5 parts of wax and 3 parts of oil that give you a very nice immersed what we call emulsion. Yeah. So what we were looking for is a very smooth curve like this, giving one bump and not 2 bumps like this. So we found that the ratio of 5:3 was brought and flattened, that it's an ideal composition of oil and wax that we have chosen for further study. Yeah? So we take up from here. And the surfactant effects, so we use various combination of lycopene powder, ratio of melting lipid mixture, and surfactant. So we have used surfactant from 2 to 6%. Yeah, so from 2 to 4%, it actually reduced the particle size, but the 6% has actually led increase in the size. Yeah, so with that, actually it led to high burst release of lycopene because of the way that the lycopene is distributed in the NLC, whereby the lycopene will be released from the water phase. Yeah. Now this also could be happening because the partition of the lycopene back into the lipid phase. Yeah, so that is also can cause that the lycopene will be released in a very drastic manner. Yeah, I'm just adding in this table here for you to look at the values while I'm going through. So the average particle composition will be 88% of water, 4% of surfactant, twin 80, and then 3% of the CMC was chosen as a basic on the basis of the particle size and zeta potential. So if you look at that, 88% and 4%, okay, and then the surfactant CMC is 3%. Yeah, so we have got CMC is 3%. Yeah, around there. What we are looking here is the charges in this combination. Yeah, so the charges should be less than negative 30 MV to give a good stability for this combination. Yeah, so we have got that the one over here, the WT2. Okay, so that actually gave you the best chosen formulation. Yeah. Now we're testing on the CMC. So the CMC increases the viscosity of the formulation, which even with a little bit of increasing the concentration of CMC, it improves the bioactive solubility in the lipid matrix. So a smaller particle will be is produced. Yeah. So now after 8 weeks, yeah, so this particle remains, yeah, so remains in the same size, could be due to the negatively charged formulation, which the repulsion is there, so it doesn't let the formulation or the component to agglomerate to form unstable or larger particle. Yeah, so the repulsion that given by the negative charge on it is actually added to this product. Yeah. Okay, so now this is the how the formulation looks like. So later I will show you the picture. Now here we have done the TEM for this unloaded and loaded lycopene. So what we have found was that both of them are the same morphology, where you get spherical shape. However, the one that loaded with the NLC shows a bigger size. Now the drug delivery part. So before that, I show you this is the formulation that we have got. So you can see it's very stable. It's not separating into 2 layers here. So if you're separating into 2 layers, it's not good. So in order to obtain this, very stable nano emulsion, so the wax and lipid ratio is very important, as I show you the DSC curve just now to form the one bump. So that is the one that lead to this nice formulations. Yeah. So now we need 10 milligram per day of lycopene in order to protect against the UV radiation. So we try to formulate the topical formulation with lycopene in order for this protection. So in that formulation, actually, we have got the, we have added from 0.25 to 2.25 milligram of lycopene in the NLC1, NLC2, and 3. Yeah? And this formulation actually gave the entrapment efficiency about 95 to 98% of this. So it's very good that a lot of the lycopene that you have added actually, you know, entrapped in the formulation. So this could be the highly lipophilic nature of the lycopene that entrapped in the lipid matrix. All right. So and also if you look at the release of the
Pushpa,
yeah.
Can you wrap up the presentations?
Yeah,
for
sure.
another 2 or 3 minutes? Thank you.
Okay. So now this release of lycopene, definitely when there's increase in the lycopene concentration, so there's a increase in the release. But however, with the pure lycopene, you can see it is drastically been released. So there's a sustained release of lycopene in this formulation. Yeah. So that's what we wanted to achieve. Now this work is actually has been published. So you can get the reference here. So it's in Carbohydrate Polymers Technologies and Application. Yeah. So to round up this material, which is lycopene loaded CM carboxymethyl, oil palm empty fruit bunch cellulose, nano-structured lipid carrier has a potential use in the drug delivery system or in other pharmaceutical applications. Yeah, so for betterment of human health. Right, these are my other works with other polysaccharides that I have used, also used for the slow release fertilizer, tissue engineering, and we have got capsule patent and used in heavy metal dye absorption and release study has been done, drug delivery. Okay, so this is from the other polysaccharides. So these are my PhD students. Some have graduated and current students. So the one that highlighted in greens are presenting in this symposium, right? And these are my collaborators. So this are my students here. And these are my collaborators in Singapore, IMRI. And here is from Sunway University, Dr. Ronald. and the white people are all from Australia. Okay, so from Monash University as well as Swinburne University. Dr. Mansur from UPM, Dr. Raman and Degaraj from, they're both professors, they're from India, and Prof. Lim, Dr. Puria and Dr. Saravanan from UAE. Okay, so they are my collaborators currently. Dr. Puria is at School of Engineering, Monash University, Malaysia. Now, these are the funds that I've got from the government to achieve all my results here, okay, to actually carry out my research work, yeah? So the one that highlighted in greens are all government grants. Yeah, thank you so much. Thank you for listening.
Yeah, for these fruitful sharings and great achievements. There is one question from the floor. What is the plannings to do dermals or transdermal applications in future? It is the in vivo studies will be applied in this related study, and does the Monash has the in-house expertise to do so? Thank you.
Okay, so actually the further study for this work is actually we have done we're going to do the in vivo experiments. So we have got the animal ethics approved, and currently I'm looking at the resources to do this work because my student has graduated from this work, so I need to look for another student to continue this work. Yeah, so it's actually in the pipeline.
Thank you, Dr. Pushpa, for the presentations.
Yeah, thank you so much.
Now, I will move to our next speaker, our keynote speaker. I'm pleased to give a brief introduction to this Associate Professor, Dr. Poon Wai Chin. Right, Dr. Poon is an Associate Professor of Economics in Petronas UTP. She is the Honorary Secretary of the Malaysian Finance Associations, editors of Cogence Economics and Finance, editorial boards for high-tier journals. Her research interests are applied economics, business economics, financial economics, sustainable development, tourism, and education. She is currently working on the circular economy within the sustainable development framework. Her research excellence and impact have been recognized as the top 25% of the economists in Malaysia. So without further delay, I'm honored to invite Dr. Poon to share on the topics of biomass in circular economy. The stage is yours, Dr. Poon.
Thank you, Chairperson, Dr. Lee.
Poon, yeah, just remind here, I also see the duplicate screen from,
right.
Yeah.
What about now?
Yeah, now it's right. Okay, thanks.
Okay, great. Okay, so greeting to everyone. First of all, I would like to thank Dr. Lee for your brief introduction about me. And I would like to thank the organizer, Prof. Chan, as well as Dr. Pushpa, for inviting me to share the information in this second E-Symposium on sustainable transformation. And today, I would like to share with you some of my thoughts on the concept of circular economy and the significant role of biomass in circular economy framework. So this work we do together with Lim Chan Shin. He will also present after me for another topic relevant to circular economy as well. So sustainable development, it is such a buzzword that all of us are constantly being reminded by the media, and it has evolved into global pursuit. However, I would like all of you to take a pause in your busy schedule and then think about what it's actually meant to you. So in 1983, way back perhaps when some of you have yet to be born, the ex-Prime Minister of Norway was commissioned by the United Nations to chair the World Commission on Environment and Development. Now, this World Commission on Environment and Development was a sub-organization of the United Nations, UN, that at the time aimed to unite countries in pursuit of sustainable development. That was when the movement of sustainable development began. And the report from her commission named Our Common Future was published in 1987. Yes, you heard that right. Just now I mentioned about the ex-prime minister is a lady, and her name is Dr. Gro Harlem Brundtland, and therefore the report is also known as the Brundtland Report. So if you have time, I do recommend you to spend some time to read the report if you have not done so. So when I first read it, it has given me meaning to what we are pursuing today in this E-Symposium, which I hope you will find your inspiration as well. Now, the sustainable development movement has evolved over the years to what we have seen today as the United Nations Sustainable Development Goals 2030 launched in 2015. And nowadays, it is part of any public listed companies worldwide responsibility to report their respective corporate sustainable development activities in the form of ESG, which is E stand for environmental, S stand for social, and G stand for governance. So within the palm oil industry context, not to say that other goals are not relevant, but a typical circular economy will most probably involve sustainable intensification activities that contribute towards these goals. So goal number 15 is what I would like to draw your attention to. And I would like to bring you to specifically to this goal 15 only because it covers protect, restore, promote sustainable use of terrestrial ecosystem, and halt and reverse land degradation, which the return of palm residue and oil palm biomass is pivotal in sustainable development in this area. So what is basically circular economy? There are many definitions and many different interpretations to circular economy. However, in general, a closed-loop industrial system, or we can say the value chain, where resource input can become restorable, restorative, and regenerative, minimize whatever waste leakage by closing the material and energy loops, describe the circular economy. For oil palm industry, the definition promoted by Ellen MacArthur Foundation since 2014 is most appropriate in my opinion. And Ellen MacArthur Foundation said that a circular economy model needs to have at least 3 key principles. First is design out waste and pollution as much as possible. 2 is to keep the biomass waste stream in use. 3 is the most important component, is that it has regenerative factors and component. And regenerative natural system would mean circular economy that goes towards regenerative agriculture. That all this can translate into ESG, okay? Environmental, social, and governance, ESG, at the company level or corporate level. So the acronym ESG was coined in 2004 to 2008 in the report named Who Care Wins. This was initiated by the United Nations again, the Secretary General and United Nations Global Compact in 2004 in collaboration with the Swiss government. And this initiative was endorsed by 23 financial institutions collectively, representing more than $6 trillion in assets. The IFC, okay, and the World Bank Group were among the endorsing institutions. So this report commissioned by IFC, IFC stands for International Finance Corporation Advisory Services. They seek to influence, to support, to enable capital markets stakeholders to better integrate these 3 component ESG into capital allocation, portfolio management process, to frame expectation around the company's environment, the company's social perspective, as well as corporate governance. So it is now guiding principle of some sovereign investment funds, such as Norwegians, where the funds will and can only invest in businesses that exhibit and meet the fund's ESG investment criteria. So this could be another topic. We are not going to talk about this issue today because that will be a lengthy discussion. So it could be another topic for another day, but not today. Right, now we dive in and look at the detail. The E in ESG means what most of us talk about today, environmental criteria, which includes the energy the business takes in and the waste it discharges, the resources it needs, and the consequences for the environment and living being as a result. Not least, E encompasses carbon emissions and climate change. So in the oil pump context then, what is the role of biomass? What sustainability intensification activities can improve environmental and economic performance for the business, and therefore the oil pump upstream industry as a whole? The S, as in social criteria, addresses the relationship the company or the business has and the reputation it fosters with people and institutions in the communities and in the oil pump value chain, especially when you have independent third parties like the smallholders involved. It also covers labor relations, diversity, inclusion, and so on. The last component is G, representing governance. It is the internal system of practices, controls, and procedures the company adopts in order to govern itself, make effective decisions, comply with the law, meets the needs of the external stakeholders. Every company, which is itself a legal creation, requires governance. So having effective ESG elements by combining all these E, S, and G elements actually incites better performance for the business and not just expenses item just to meet the compliance report. The palm oil industry has been in the limelight over the years, especially our country as well as Indonesia. And it does have pertaining ESG challenges, given the degradation of soil conditions due to aggressive chemical fertilizers input and decrease in plant health and yields as a result of deterioration of soil conditions, which leads to our environmental and sustainability issues. Given the significant percentage of the planted palm oil estates are owned and operated by the small holders, and the soil condition, yield performance greatly affect the livelihood of these smallholders. And uplifting the yields, bridging the yield gap is one of the primary challenges. And we focus, this is also one of the focuses the industry policymakers are currently addressing, which is about, we are looking into the rural community's social well-being. And on the other hand, given the pragmatic economic needs of respective palm oil producing countries, and the fact that palm oil as a significant food and renewable resources being 35% of current global vegetable oil and its oil yield productivity of more than 6 times the next alternative seed oil, certain palm oil consuming countries and NGOs approach of boycotting palm oil is not an option at all, because this will inevitably result in more land needed to be converted for these alternative crops in order to meet the growing demand. So using Malaysian oil palm 2019's data, the fresh fruit bunches, or FFB, yield on average was 16.66 metric tons per year per hectare. And there were 5.9 million hectares in 2019. For a typical 45 metric ton per hour FFB processing capacity palm oil mill, it will need 12,000 hectares to supply 200,000 metric ton of FFB. And there were 452 palm oil mills in 2019. 3.33 metric ton of CPO were extracted per year per hectare and shipped out of the oil palm upstream ecosystem. And the biomass waste from the day-to-day operations consists of oil palm fronds that were pruned during harvesting predominantly. The palm mesocarp fibers, palm kernel shell. These are used as a boiler feed for the palm oil mill to generate steam and power. And therefore, they are removed from the oil palm ecosystem. And the EFP, pomade, palm decanter cake, palm boiler ashes needs to be treated. When the oil palm fronds are left in the estates as inputs for soil organic contents, which is a good sustainable practice that fits into circular economy principles, and the volume is significant. 10.4 metric tons per year per hectare is significant, right? However, this practice alone could not arrest the land degradation trend caused by the aggressive chemical fertilizers. The rest of the biomass waste are either disposed by removing away from pond, open lagoon ponding system, and biogas capture for pomade, and EFB for mulching, and or composting. So returning the composted biomass back to the estate and mulching exhibits circular economy principles. So what I have described represents the majority business as usual practices of the Malaysian and Indonesian oil palm industry. And there are many other sustainability intensification development options for this biomass, such as biorefinery, long fiber, etc. And all these waste treatment mechanisms have various degrees of techno-economic challenges, which results in 125 POM adopted biogas treatment despite regulatory pressure, out of which 30 are power generating and connected to the national grid, and 76 composting plants. I will leave the discussion on techno-economic challenges of various valorization options to my fellow researcher who is presenting after me. By the way, mulching is a serious concern as well, given the current severe labor shortage, especially during COVID periods. A lot of foreign laborers have been sent back to their home country, and lots of licenses have not been renewed. So there were actually a serious labor shortage issue right now. And for smallholders, usually do not have access to this biomass such as EFP. The strategic role of beneficial microbes, biomass, and bioorganic fertilizers. And for those of you might not be familiar with the term bioorganic fertilizer, so BOF, bioorganic fertilizer, are composted biomass that contain high concentration of beneficial microbes colony due to the waste treatment process. It is well documented fact that soil fertility is closely correlated to presence of beneficial microbes colonies, fauna, flora, okay, in the soil. These microbes need organic matters and adequate moisture in order to survive and propagate. Large-scale BOF, bioorganic fertilizer production, also faces two challenges. Number one is the availability of large volume of consistent biomass as feedstock. Number two, to ensure a large CFU count of targeted microbes, the composting process or production process must be optimal for the growth of these microbes, precise and controlled. And the palm oil industry has a history of unsuccessful windrow-based composting processes due to the inherent uncontrolled composting environment, especially for bioorganic fertilizer production. That often produces substandard or uncomposed BOF due to manual processes intervention and the uncontrolled composting environment. And just for your information, the composting periods can range from 40 to 90 days. A good example of biomass in circular economy is of an in-vessel core composting plant that process all the biomass. That is EFB, pomade, decanter cake, boiler ashes, and then turn all this into BOF, which in turn to be applied back to the estate for long-term soil remediation. And this particular core composting plant, which has been operating for 10 years from 2010 to 2019, occupies 1 hectare of land size next to palm oil mill. It consists of biomass pre-compost treatment, preparation, control environment, composting chambers, curing base, and an on-site bioplants that supply the beneficial microbial formulation for BOF manufacturing. After curing and bagging the BOF, are shifted back to the estates using the same transport vehicles that have unloaded the FFB at pump. The control environment composting process takes 14 days in the chamber instead of the usual 40 to 90 days for the windrow-based composting 8 months after BOF applications. The soil conditions have improved significantly due to the beneficial microbes introduced by the BOF into existing front heaps, with more than 40% increase in the cation exchange capacity. Now, the cation exchange capacity is an indication of plants' nutrient absorption efficiency. Now, from this diagram, you basically can observe plants' nutrient absorption rates here shows the emergence of earthworm colonies and the increased feeder root density of the tree crops. It shows improvement in all these so-called indicators. Okay, the role of palm is the key in the circular economy model and framework, as it can provide the power and local network infrastructure for the local communities. With the integrated waste treatment complex that treats all the waste stream into renewable energy and BOF for long-term soil remediation. With the local renewable power and network infrastructure, we can envisage the deployment of Industrial Revolution 4.0, precision agriculture, and local shared digital platforms for supply chain automation with SME, small medium enterprises. With the upcycling of biomass that improves soil ecosystem and better yields. So overall, upcycling biomass as bioorganic fertilizer demonstrates a use case of biomass in circular economy that can generate revenue for economic sustainability and soil revitalization for sustainability intensification. Regenerative agriculture is crucial in bridging the yield gaps, and biomass is the key. And what are the potential policy implications? The potential policy implication can be embracing the paradigm shift towards circular economy framework. In other words, upcycling biomass as bioorganic fertilizer for long-term soil remediation. It can be the commonly acknowledged sustainability intensification platform, bridging the producing countries' pragmatic legitimacy and the consumers' countries' moral legitimacy towards sustainability intensification for food security. Building sustainability and circular economy value chain is a strategic policy direction in addressing post-pandemic revitalization, or what we call resilience methods, in order to cure all these so-called climate change risks, or at least try to reduce the risk and social costs. And for those who are interested, here are some of the literature that supported our findings. With that, thank you very much for your attention. That's all from me. And my sharing session is more on from the business angle, not too much on the lab work, or not too much from the engineering angles. So I hope that will not bore you too much, right? Thank you so much. And back to you, Chairperson, Dr. Lee.
Okay, thank you very much, Dr. Poon. Indeed, it is a very interesting topics regarding this techno-economic analysis. We have different angles and point of view in this oil palm biomass usage. So any questions from the floor? You may channel your questions through the chat box or Q&A box, as well as you can ask lightly in this webinar. Okay, before that, I have one question to Dr. Poon. To your understanding, where is Malaysia's today on these developments from oil palm biomass industry in the context of sustainable developments and circular economy?
Okay, frankly speaking, circular economy framework, this model is still relatively new. As you can see from many governments' reports, or even annual reports, they also just recently incorporate the elements of circular economy framework. So in other words, this is relatively new here. And many of the industry, including whatever agricultural sector, easily we can apply this model. Yeah, so I will say we are still in the infancy stage, right? So a lot more research needs to be done before we can confidently say how well have we done using circular economy model in regenerative agriculture, particularly this area. Thank you.
Okay, thank you. Then another question, which is from Dr. Kwakit Singh. It is he's asking, is it all the biomass should keep or use within the plantations and milling?
Okay, so thank you for your question, Dr. Kwa. Basically, ideally, all biomass should be reprocessed so that it can be reused back in the plantation area. Ideally, it should be. Okay, but we also have to consider factors like the distance of this biomass processing plant, as well as the palm oil mill. If there is quite a distance, so in that case, that could have a large cost involved. So then it will not be the ideal anymore. So a lot of factors we need to consider. But your question is good in the sense that yes, we should actually to use all biomass, produce it, and then try to produce some value-add product. Just like bioorganic fertilizer is a value-added product. We can reuse it and ask, maybe perhaps it could be just like a subsidies. Governments can consider. Governments can just buy this DOF and then pass it to small planters for them to use it. Small planters, they do not have a sufficient so-called budget to buy BOF. For them, it could be additional cost. So therefore, they are not willing to do so. So what the governments can do is perhaps buy it and then after that distributes to the small planters for them to reuse it. And this is what we call a circular economy model, part of that. So I hope I have answered your question, Dr. Kwa.
Okay, so thank you, Dr. Pons. So I will move to next invited speaker, which is Mr. Lim Chan Shin from School of Chemical Engineering, Monash University, Malaysia. Mr. Lim is an entrepreneur and structures investment professional with 33 years of experience in structures investments, M&A, and sustainable development. His key areas of expertise are regenerative agriculture and fintech, He provides high technology industry related advisory for fundraising in Europe and Hong Kong equity markets. He has 2 degrees from Monash University, Melbourne, which is the first is Bachelor's of Engineering degree in Electricals and Electronic Engineering, and the second is Bachelor's of Science degree in Computer Science. Apart from providing advisories to regional private equities, he's currently pursuing his PhD in the School of Chemical Engineering. So without further delay, I'm honored to invite Mr. Lim to share on the topics of Techno-Economic Challenges in Biomass Valorizations. So the stage is yours, Mr. Lim.
Thank you for the invitation to present some of our work that I have done with Prof. Kun and of course with Prof. Paul as well in the chemical engineering. I think there is a lot of challenges in the biomass, and one of the questions that we asked actually quite pertaining, and I will try to add some my view, my perspective on some of the questions that's been asked in Prof. Kun's sessions. Okay, now circular economy legislation in Europe has actually resulted in implication to our oil palm industries. All right, it is such an important strategic decision that the European has taken now, especially in 2019. They have legislatively, it means it's passed as a law in European countries that they need to do what we call the Green Deal. Yeah? So adopt new proposals to stop deforestation, innovate sustainable waste treatment, and make soil healthy for people, nature, and climate. That resulted in some of the legislation that says that oil palm is not suitable for energy use or for biodiesel, and it will be phased out in European economy as a renewable fuel. All right, and as late right in the middle of the pandemic, the Europeans actually believe that for the great reset after the pandemic, it has to look at a clean and circular economy. That's why they launched their new economic action plan at 2020 CEAP. Yeah, and you look at the statement that they have made, it's actually a strategy to have all European soil restored, resilient, and adequately protected by 2050. All right, so this is a positioning as well as a very structured strategy that has been ongoing, and it pays to be circular. If you look at the keeping the material in the loop and being restorative and regenerative, as what Prof. Poon has eloquently you said just now, I think it's something we should look at. And by the way, you look at Europeans, 95% of the soil foundation for the healthy soil is a foundation for 95% of the food, and yet 70% of the soil in EU are not in good conditions. Okay, so within the palm oil sectors, we are having the same issues of the aggressive modern agricultural practices. And I'm taking this slide out from Prof. Poon and trying to answer, looking at why our palm oil industries is in the way that we have been practicing for the last 100 years now, more than 100 years now. We celebrated our 100 years anniversary in 2017. Yeah, actually sustainable in the terms of if you look at it, if you look at the oil palm fronts, actually is within the circular economy, and then you have the EFT in mount and put back. But of course, proponent says that the mounting is it's concern now. Actually, not many people actually doing it. But key point is 125 out of 452 palm oil mills actually have biogas. And out of this, for the homemade treatment, yeah, for those people that may not know what biogas means, basically is capturing the biogas production generated from combined treatment. And of course, only 76 composting plants actually being built. And how many of these are actually being running now is still a question mark. Yeah, and the land gratification trend is definitely that without a doubt. And of course, now our country has going through oil palm replanting, and there's also a significant amount of biomass coming up. 74.48 metric ton per hectare of oil palm being replanted. So you can imagine this huge amount of biomass actually and goes back to the soil. Yeah? And I'd like to take this opportunity to answer one of the questions. We need to have all this huge amount of biomass returned to the estate. The answer is perhaps not all, perhaps significant enough that we can make sure that we do have a regenerative element back to the whole ecosystem. It's not. It's like people say, you kill the goose that laid a golden egg. The land that we have are degrading to the point whereby it may not be economically sustainable to proceed and keep the stick going. Okay. Palm oil mill process. I usually would pause here and ask how many people in the audience has actually worked and spent enough time in a palm oil mill itself and actually gone through the processes and see how where the waste streams are each being generated. This is a knowledge graph, by the way, from the studies. It is basically looking at various processes, and this process has been there years. Yeah, and based on some of the presentations earlier in this E-Symposium, especially Tan has mentioned that the PKS, which is palm kernel shell, and palm so-called fiber or palm patch fiber, as the term being used, are actually being reused back as a regenerative renewable energy for the boilers and the steam required for the sterilization of the fruits. And of course, as I mentioned just now, just like the palm kernel, oil palm fronds are actually re-feed back into the soil as soil organic content. So it is regenerative element already there, but it's not sufficient enough because of the excessive chemical fertilization that we have adopted over the years. Because of we have higher yield, especially now, we have reached a historically high in terms of CPO, 6,000 and above. Even all this, you need to really look at, even at this level, at the palm oil mill level, there is a lot of wastage in terms of, not just in terms of biomass, but also in terms of the energy, the waste heat that they have generated and so forth. Okay? And whether that is going to be the case going forward or not is a lot of area for research to look at. Can easily optimize the palm oil mill process itself to have less waste being generated and reuse some of the waste that is currently produced. If you just digress a bit, if you look at it, OME actually consists of 3 liquid waste streams, yeah. And while I'm talking about this, some notes for all of us. FFE actually cannot share of nutrient being removed. Actually, it's 51%, 34%, and 37% in terms of NPK. Yeah. And in terms of actual NPK in the CPO, actually it's very small. So most of the nutrient fit into our chemical fertilizer cost, which is 45% of FFE production, actually stay with the waste or biomass. Okay, so what is the business as usual? It applies across, especially in Indonesia. This seems to be the most practices being done. Mulching are being practiced, as I mentioned earlier, as Prof. has mentioned, especially in large plantation group, whereby they control the mill as well as the estate. But for independently operated palm oil mill, such practices may not be applicable, or rather possible, because of cost involved and logistics involved, and especially true for Indonesian market. So waste treatment implementation for meeting mandatory compliance purpose without sustainable, resilient economic input does actually lead to neglect. And it is one of the reasons why Europeans are looking at this industry as quote unquote not sustainable from that perspective. Yeah. And certainly if we can have a circular economy model and practices entering into the oil palm industry, then perhaps the global will look at the oil palm as a sustainable agricultural product towards food security as well. I forgot to mention a bit. By the way, Europe is not the only country, by the way, that actually legislative circular economy as part and parcel of their operating rules and regulation within the country. At the economic bloc, China. China also legislatively put green growth strategy similar to Europeans. In fact, the lead drive earlier than Europeans. They have legislatively put in circular economy way back in 2016, right? And Europe now they're put up as 2020. There's something off. But this is the typical business as usual. Certain foundations have good management practices would actually spend the effort to move the ESSTPOW amount back to the estate. But this practice during these 2 years of pandemic no longer become viable, and hence is a factor to look at. If we want to build resilience in the ecosystem, function cannot be the only solution that is applicable. Okay, I will look at the techno-economic challenges in one of the huge biomass, which is palm oil mill effluent. If you can see here, because of this registration, 2014, all palm oil mill must replace the traditional, what we call open lagoon ponding system with other alternative format treatment system that resulted in greenhouse gas emission reduction. Okay. Now, for that, it only left with what you see today as the viable and also producing practices that's out there that can be used in circulating the waste stream. And the biogas is where it's being captured. Out of 125 palm oil mill that's been installed with biogas, more than 50% of the biogas are flat. Okay, as of 2019. And this is something that we all need to look at. I have seen some very interesting presentation here this morning on some of the use of the waste stream or the biomass. But we also need to look at all this technology when you come to the point of commercialization, and there is inconsistent feedstock that is very prevalent in the palm industry, which is you have high crop season, low crop season. When you design a waste treatment, you expect consistency, but actually that's not the case. And without a connection to a national grid whereby you have a feed-in power purchase, usually the most appropriate or lowest cost of making the compliance is just build a covered lagoon and just flare it. Okay, EFP has lots of applications, lots of usage. I am actually quite excited about what are the applications required. To look at a circular economy, EFP has one role that, in my opinion, it is vital, which is recycling back as EOF, because it is a medium of transfer for beneficial microbes back to that state to remediate the current soil condition. Based on the current trend that we're seeing now, just having the biomass from the oil palm frond is not enough. So there is a need to use EOF as a medium of transfer to put in the necessary microbes back to the soil. Now, the news is you do not need to have all the EFP to do that. A certain amount to fit in to activate and work on the biomass from oil palm frond would do the job. What is that optimum amount? It's also some of the studies that I can foresee that we need to conduct. We have yet to do that, but we know for a fact that this works and the yield goes up and soil system increase. But how much do we need to introduce the microbes back to the land? Something we need to look at. Right. So in the EFP, they have other options. Like for example, in the early years, you have the biomass power plant down here, and logistics is one of the key issues that actually make biomass power plant challenging to operate. To have a minimum scale of production, we need more than EFP, feedstock from EFP for more than one palm oil mill. Okay, mulching, as I mentioned, it's good to have, but only partially used by a lot of the conditions because of labor costs, and also there's a need to properly plan the application of mulching. We know composting has its challenges, and logistic cost and inconsistent supply of FFP is always has to be a major consideration for any of the valorization options that you guys are contemplating for this industry. By the way, biochar is a good option that can be produced from oil palm trunk, EFP, and it has very, very good potential as a soil remediation component. Yeah, but something needs to be looked at. Okay, I will just zoom down on one component of the EFP, which is called composting systems. Windrow, both outdoor and covered, has its challenges. The biggest challenge, of course, is the inconsistency in the production, which causes that you do not know when the process is going to finish or how are you going to manage the processes. And this would have an impact on the economic performance of any of these projects. As you all know, we may have good technology, but if the process and all that is not going to allow the owner of the business to make money, it's not going to happen. So processing skill and volume, pricing, quality, efficiency is important. Stock consistency in quality and supply has to be there. Logistic and distribution and applications. Yeah? These are key techno-economic factors that you have to factor in whatever work that you are doing for that particular industry. If the oil palm industry is where you're targeted at, this is something that you must factor in. If not, we can do a lot of very good innovation, but it's not going to reach the market. Yeah, and in this particular case, the composting system that you deploy have to look at, and this is a fact. Operators tend not to venture into eco services, and they are not interested in sales and distribution of compost. They just want to make sure that they process all the FFP to produce the OER that they need. Yeah. So, and of course, in this particular case of bioorganic fertilizer, is a conflict of interest with existing chemical fertilizer supply chain. So something to look at. On top of this, to apply the BOF back to the estate, you also think about fertilizers and how is that being done. It is not a replacement of chemical fertilizers. It actually is, as I mentioned, it's a medium of transfer for the microbes to be put back into the estate within the biomass already there. That means the oil palm front, and there are oil palm trunks available, you can put it there as well. And this component need to involve people that understand soil ecosystems. Yeah, it is a lot of research being done over the years, over the last 3 decades. And there are a lot of applicable beneficial microbes that is known. But so far today, there is not a structured way of going in. And the Europeans are leading in these sectors, as well as the Chinese. These are the 2 major agricultural blocks that are looking at food securities. Yeah, and it is something that we need to be aware of. Precision agriculture is important. We have to know the data, how well our crops are doing, what are the soil conditions, and palm oil mill actually have renewable energy that can actually power the necessary data infrastructure within the local community. Yeah, on its own. Something to look forward to. And of course, plant health, melanoma disease is one of the big factor in the palm industry, and it's treatable. There are microbes that can use and all that, but usually it cannot be put into an infrastructure that can deliver it on time and in large scale. I will not go to each challenges in each one of them, but this is a result of thematic interview with practitioners, with over 50 of them. They are all seasoned, over 20, 30 years in the industries, and the issues are actually not technical. Technical for being a circular economy is that well matured, but it's all to do with economic factors, the cross-disciplinary knowledge deficiency that we can see, and all aware that upcycling is good, but there is no incentive for them to do it between the palm oil mill and estate because they are owned by different people, for example. One of the approach, of course, is to integrate both the biogas, produce the power to power the industrial processing plant. This is one of the suggestions. They actually produce the fertilizer goes back to the estate. Now, that would not solve, but actually provide economic impetus for biogas plant to have a sustainable, because you have a local demand of power, and the power cost can be recovered from the sales of the BOF. Yeah, do by all means contact myself and Professor Poon and Professor Paul for more details of this if you guys like to look at it. And last, I want to just close it with what Prof has said. It is a circular economy, and 2 things must be there: revenue generation for economic sustainability. If the process that we do are not revenue generating, then you have issues. And of course, it's enough to go back to the loop to make sure that the soil revitalization is there. Okay, and last but not least, I just don't leave everybody with this slide that Prof has mentioned out. Reversing land degradation trend. This case study actually on this control, which is using the existing chemical fertilizer regime, not using the BOF as a soil remediation. Over 10 years, they actually increased to 200 tons. But more study required to look at other estates as well. But this is 40,000 hectares, yeah, over the past 10 years. And regenerative agriculture actually is where we can reach the yield. Palm oil trees can survive more than 30, 25 years or 30 years, provided that the height of the trees can be managed so that the harvesting can be done. But the difference of the yield gap is where we can pick it and still able to meet future market demand for the oil, palm oil, without incurring new land for replanting. Okay, I will leave it there. Some of the references. Thank you.
Thank you, Mr. Lim. Any questions from the floor? Okay, Mr. Lim, they're very interesting topic from you because it gives us a new perspective in terms of this techno-economics, point of view, especially for all as a researcher in inventing a new type of biomass products here. So I have a concern here. We know that the biomass is rich in all these palm plantations, and we have a high numbers of palm biomass, right? So however, the palm biomass, the price, even the feedstock is under controllables by certain of these respective bodies. So in these situations, is it the palm biomass products still meet the balance between the production cost, environmental concern, as well as the user interest?
You're actually right there. When you do a valorization project to make value add onto the biomass, okay, by processing it, as I mentioned, to biorefinery, to some like what Dr. Pushpa are trying to do, as well as of some of the discussion that we have. The end product doesn't commensurate with the feedstock. Okay, just like the Topotrino, for example, that we talked about this earlier this morning. When the CPO is 6,000, and here you are, you provide the supplement for health supplement for using vitamin E, then access is going to be an issue. So when we look at the way that we look at a circular construct for any economy, you need to look at the cradle-to-cradle approach, especially in agricultural base, in this particular palm oil. Yeah? But as long as we can have enough to sustain and maintain the sustainability of production of the sources, which is in this case land and the soil systems. It is a very, very urgent issue, and it has been identified not just by us, recognized it in palm oil, but globally now. It is a trend that circular economy actually pays. Previously, people say, oh, I do circular, recycle, actually it's a cost. But if you do it right, it actually pays. So if we can find ways to look at the biomass to improve the regenerative nature, as I mentioned, biochar is one. It has very good property in biochar. And I left out talking about oil palm trunk because that particular biomass is a lot. But it is not part of a regular operation. It's only available during replanting, right? A large amount. So you need to look at that. So, but you are right. It is going, the biomass in time to come is going to be a lot of value attached to it. At the moment, it seems to be, it's a waste. You can have it for free because nobody do anything about it. There is a cost to dispose of it. But in time to come, that biomass is going to cost money. And that's why I'm saying that the owner who owns the biomass, does it belong to the farmers that produce the fruits in the first place, or actually belong to the palm oil mill? But in this case, the legality is they bought the fruits from the farms. Smallholder, so whatever is left belong to palm oil operation. So asking that to be back is a separate issue. Yeah. But
Thank you very much, Mr. Lim. Yeah, so now we are moving to another next invited speaker, Dr. Asha Salemma from School of Engineering, Monash University, Malaysia. So Dr. Asha graduated his bachelor's in chemical engineering from University of Pune, India, master in chemical engineering and PhD in mechanical engineering from University Technology, Malaysia. He did postdoctoral at University of New Brunswick, Canada. Currently, he is working as a senior lecturer and course director of Master of Applied Engineering at Monash University, Malaysia. Dr. Asha's research interest is in renewable energy process design and developments of thermochemical system, microwave processing, energy efficiencies, and sustainability. He's working on various industrial and government projects. Dr. Asha has published more than 60 articles in the international reputed journals and conference with H index of 23. So the floor is yours, Dr. Asha.
Thank you very much, Dr. Lee, for that kind brief introduction. So today I would like to present my presentation on integrated microwave steam sterilization technique to add some value to the loose oil palm fruits. So this is my presentation today. So we all know about oil palm milling process, already mentioned in the previous presentation. I would not go into all the details of the palm oil mill process, but I would focus only on sterilization. It is the first step in milling process. It has not been much changed, the technology, in the past 50 to 60 years. So they use, basically in the industry, in palm oil mill, they use high pressure steam and temperature of around 140 degrees Celsius for a long period of time, maybe 1 hour plus, to sterilize the palm oil, fresh fruit bunches and loose fruits inside this different, what we call as, either it can be horizontal type of vessel, process vessel, or it can be vertical process vessel. And the whole cage, basically you can see here is, just give me a second. So you can see here this sterilization, the whole cage is put inside the vessel. Okay, there are tons of fresh fruit bunches inside this vessel that gets sterilized. Of course, it will take time to get sterilization, but this is the first step in the palm oil milling process. So what happens, because we use steam converts into water, it takes away a lot of chemicals and other things from these palm fruits, and it generates palm oil mill effluents. Okay, you can see here, this is very typical for most of the palm oil mill, and it is an environmental liability for most of this palm oil mill industry, and it is a headache to dispose it off in a very controlled manner, and it costs a lot for the palm oil mill industry. Of course, there are many methods coming up, technologies to convert this foam into other kind of products, or to use it, to reuse it. Okay, so sterilization process, what it is a process of terminating kinds of microorganism in the palm fruits or any other material. It is an essential pre-treatment process in the crude palm oil extraction, and it has number of objectives: to deactivate lipase, break up oil-bearing cells in the mesocarp, so that the mesocarps becomes conditioned. The top, this one, this yellow color you see here, it becomes conditioner because of the sterilization, and it softens the fruit, so it can be easily detached from the fresh fruit bunches, the big bunches there. So palm oil sterilization technologies currently used in the industry, as I mentioned, is the horizontal vessel, process vessel. They are using vertical, so mostly are horizontal one. There are verticals also in some of the palm oil mills. There are some continuous vessels also, but very few. An alternative or new type of technology, I can say, not new technology, microwave is already there, but a technique can be used to sterilize the palm fruit is actually microwave. Okay, microwave irradiation. Now, all these conventional technologies, they are pretty much on heat transfer conventional type, which is based on contact type of heating. Contact means when they come in contact either with the wall, heated wall, or the steam, and then the heat is being transferred from the surface. From the surface, it gets transferred to the inner core of the. So what happens in the conventional type of heating? The heat comes here on the surface of the palm fruit, then it gets transferred inside slowly. Okay, so this is a conventional type of. In microwave, what happens? Microwave are non-contact type of heating. Non-contact means the heating magnetron or antenna of the microwave, it radiates, or it radiates the microwaves, electromagnetic waves, and these electromagnetic waves goes basically it gets absorbed inside the material to the extent depending on the thickness of the material, depending on dielectric properties of the material and other properties of the material, the microwave will get absorbed in the material. So it will go inside and it will generate the heat inside the material, and the heat will travel volumetrically outside to the surface, from inside to the outside. So this is the main difference between the microwave heating and conventional heating. So microwaves are basically electromagnetic waves. So there are two parts in the microwaves, electrical waves and magnetic waves. Only electric field or electric waves take part in the heating. Magnetic waves has nothing to do. It is just being created because of the magnetron, that is the magnet there. So magnet creates the magnetic waves. Frequencies between, there's a long range of frequency, 0.3 to 300 gigahertz, you can see here. Microwaves are being used in many other things, but there are some frequency that are free and we don't need any license for that, and they are known as ISM bands, that is for industry, scientific, medical purpose. So they are ISM, called as ISM bands, and they are 2.4 gigahertz that we use in our normal microwave in our house, okay, for Wi-Fi. Then we have 950 megahertz that we use for other industrial applications and many other purpose, medical purpose, and we have 5 gigahertz also frequency, which we can use 5 or 5.8, I'm not sure, but somewhere there. Other than this, all other frequencies are very much licensed, using by radar and all, we cannot use it. So of course, every frequency has its own wavelength. Heating mechanism in the microwave is more on ionic conduction or dipolar rotation. So it's basically what happens, microwave penetrate inside, the water moisture particles absorb the microwave, and because of the high frequency, they vibrate at a very high speed. We cannot even imagine the speed of the vibration of these water molecule particles inside the inside the cell, and it generates, because of this vibration of the molecules inside, it generates the heat. And this heat, that is how the microwave energy is being converted into heat, and the heat gets dissipated, I mean spread to the other through the conduction and convection in the other part of the material. Of course, microwave is very rapid heating. It's instantaneous on-off type. So if you on it, instantaneously it starts heating. If you off it, it seizes everything, terminates the whole microwave. The microwave gets terminated. There is nothing inside the cavity or the vessel. Okay, it's just the material then. If you on it, microwave immediately goes. It travels the light speed, having the same speed. Okay, so this is something advantages in most of the cases of the chemistry and material. Volumetric heating, as I already explained you, it comes from inside to outside, but it depends on the material, very much dependent on the material, you see. It's not every material will absorb, some material they will absorb very fast, some slowly, depending on the dielectric properties, on the chemical and other physical properties. Microwave are very selective, so that is another advantage. If you mix up some of the materials, so some material may not absorb microwave and other material will absorb the microwave. So maybe you have some lousy material which does not get readily absorbed by microwave, you can mix it with some other material that are very good absorption. Microwave technology, one of the main advantage in palm oil is they do not produce foaming. We don't use any steam there. So we don't use produce any foaming. So what is the problem? Why this study? Now plantation, there is a oil palm plantation. So we harvest the oil palm fruits. During harvesting, two things happens. Once we get the fresh fruit bunches that are whole, one piece, and they are in good quality because the fruits are attached to the fresh fruit bunches, and another are having loose oil palm fruits. So loose oil palm fruit, their problem is because they drop down under the tree and they are being collected. So while collection, and we use some different, somebody step up, somebody use shovels and all other things to collect it. So it gets bruises and so many other things. So the quality gets deteriorated, and therefore they have high FFA. high FFA, because of this high free fatty acids, FFA, free fatty acids, the quality of the palm oil really gets very low. So we cannot expect much good quality of palm oil from these loose palm fruits, which are dropped on the ground. You see here, fruit bunches, no problem. But in oil palm meal, what happens? They put all the things, loose palm fruits and bunches, everything inside the sterilization, and it goes for the production of crude palm oil. So there is, good FFA and bad FFA. I mean, all low FFA, they all get mixed up and it gets averaged up. So there is a high number of good palm fruits. So it gets balanced up and it is okay. But what we did is we use these loose palm fruits in our microwave sterilization method, and we want to see what happens here. So what is the drying characteristics and what is the quality of palm oil? So that was our major concern. The project scope is much bigger than this, but due to the time limitation, I will just focus on these few characteristics. So the solution was we used the palm fruit inside the microwave. So one of our method was actually, previous all the literatures, most of the researchers, they just put the loose palm fruit inside the microwave and they did the heating sterilization. I think not much has been done on the integrated type of, one of few studies has been done. So yeah, what we did is we enclosed this palm fruit inside the container. Now, why we came up with this solution was because the industrial microwave system, in the industrial microwave, they were also spreading the oil palm fruits on the conveyor belt. Loose oil palm fruits, they were just putting on the conveyor belt and they were sterilizing. So what happened at most of the time, sometimes they get overcooked, the fruits, because of the microwave irradiation and high temperature. I will come to that story again. So it gets overcooked. So this was also problem in the industrial microwave. So these all problems, when it came up, so we tried to find out the solution. What would be the best solution? So, and also the palm oil quality, by spreading the loose oil palm fruit or putting the oil palm fruit openly, like this, openly in the microwave, also didn't give much what we call as in the terms of quality and sterilization. So what we did is we tried to put in the box. We enclosed it. This palm fruit inside the box. So what happens? The steam, the natural water, when there is a microwave, this palm fruit will absorb that microwave, convert into heat. Heat will generate the moisture, water vapors. The water vapors will go inside the box. And what will happen? The steam will be trapped inside the box. So by trapping the steam inside the box, actually we are trying to implement two methods at the same time. One is microwave irradiation. One is the steam, like a conventional method to make it more to enhance the sterilization process. So actually we try to implement this to study actually what happens. So the results were there. This is the moisture content of the palm fruits. After a certain period of time, here you can see at 1 minute, 2 minutes, 3 minutes, until 5 minutes, we detected. And these are blue color lines are for the stacked layers. Now, the second thing that we studied here was we stacked the layer. You see, this is one layer of palm fruit. We stacked another on the top of it, two layers. Okay, so we stacked one layer, another on top of that palm fruit, we stacked another palm fruit layer to see what happens, because to increase the production, let's say, of the palm oil or palm fruit. So to increase the production, maybe we want to know that if we increase the quantity of the palm fruits inside the microwave, what happens? So that we call as stack layers. And then we studied the single layer. Single layer means whatever we are now using at industrial microwave, that is spreading the palm fruit in a single layer, just one layer. Okay. We saw, of course, different things. This blue color is the stack layer. You can see this little bit slow drying curve. Takes longer time, of course, because the fruits are more here. So 250 grams here. It was small lab scale study. We did a pilot scale study in the industry also. So this is like 125 grams, few fruits. So of course, the drying moisture content will differ. Okay. So optimum sterilization duration we found out for single layer and stack layer. Of course, stack layer has a longer duration because the quantity of the amount of the palm fruit. Now here, something interesting we found is FFA. Here A is the controlled no heat treatment. We just took the palm fruit and we squeezed it and we took out the crude palm oil and studied the FFA. So of course the FFA is like 18%, FFA very high. Of course, no treatment was given, no sterilization. And then we compared it with BCD. The B is a single layer. Here, this is a single layer one. Okay, the C also is a single layer but optimum. This is also an optimum study, single layer. Okay, then D is stack layer, and E is also optimum stack layer. So, of course, the FFA got reduced significantly. You can see here now all are under 5%. 5% means standard crude palm oil in the market. Okay, so that is even MV. MV is a moisture volatile content. You can see how it dropped significantly by sterilization. So 94% reduction in FFA, 75% reduction in moisture volatile content. So this is some of the appearance of oil palm fruit before and after. During microwave irradiation. You can see 32% moisture content. This is raw one from the plantation. This is 28% moisture content after microwave sterilization, partially sterilized 20%. And this is optimal heating, 15% moisture content palm fruit after microwave sterilization. So these are the, you can see the appearance, how they are being sterilized. Now, this is the condition after sterilization. Of course, this is optimum heating, 15%. So actually, in after sterilization, we are targeting 15% moisture in the palm fruit, so that that is a good value. That is the target value. Okay, and if we do excessive heating in microwave, so this is what happens. It damages the palm fruit. You see, so this is 8%, this is 3%, and this is 1% is already bone dried. So it burns, it overcooks and over sterilize. So this is not good for industry, of course. So we have to. Now this is something interesting that was not found before, because many people, they say that in microwave radiation actually FFA gets down, this thing happened, that thing happened, but what is the real factor behind it? One was the real factor behind it was that when we did the real-time temperature profiling in microwave sterilization at the industry level. So this is from the industry side. So what we did is, you can see here, we put the thermocouple inside, we inserted inside the mesocarp, inside the palm fruit at different position. We put the thermocouples, and then we did the real-time temperature profiling, and we found something interesting, that after certain times the temperature of the palm fruit reaches almost 200 degrees Celsius plus. At some point it reaches even 300 degrees Celsius. So at this such high temperature, what happens? The chemical compounds that creates FFA, actually it gets vaporizes. That helps to minimize the FFA basically. Of course, the palm fruits are always in the conveyor belt, so they are traveling. Okay, so they don't get overcooked. This one thing, and second thing is we enclose them in the box, so it gets microwave steam sterilization kind of what we call as sterilized. So this is one of the major factors that played a role in minimizing the FFA and of course the moisture content at the real-time temperature, because when we were doing an industrial microwave, nobody detected previously that, okay, what is the actual temperature at the real condition of the microwave, because we were just expecting that, okay, why it is overcooking, what is happening, and why the FFA is good and all. So there should be some factor behind that. And in industry, of course, the temperature, the industrial temperature is somewhere here, 140, 150 degrees Celsius. In the oil palm mill, that is 140 degrees Celsius, the steam one, conventional one. So it does not reaches up, you see. So lastly, the palm oil quality, we compared with single layer, sorry, here, single enclosed means in the box, microwave steam here. This is microwave steam. This is stack layer, 2 layers. Stack layer enclosed means microwave steam here. And we compared with standard quality CPO crude palm oil in the market. And we found that, see, this is the maximum is 5, it should be FFA, and we are well below the standard quality. So we can convert the loose oil palm fruit, which have no value maybe or high FFA. If you want to do it only loose palm fruit, maybe it's not good for crude palm oil production and also the refinery process. But if we convert this using microwave, we can really get a good palm oil in terms of palm oil quality. Moisture volatile content also, you see, it's well below the standard peroxide value is 0. It should be 2 maximum. Aniline value, all these values, some of these values are really important because they contribute during what we call as during the refining process. So that values should be somewhat either minimum or maximum. So that is how we this study helped to get a good results and interesting results. We will be communicating in international journals soon. So I acknowledge NIPO, Monash, Institute Chemistry, Organizing Committee, student staff who have helped us, Science Survey, Research Carry Island, and funding agencies. Thank you very much. We also have Master of Applied Engineering course launched this year in 3 specialization: energy sustainability, industrial and robotics, and oil and fats processing. So this is something very interesting for science background students and even engineering background students to come and get this opportunity and to skill up their enhance their skill in this oil and fats processing and other specialization. Thank you very much from my side.
Thank you very much, Dr. Asha. There is a question from the floor from Dr. Kwa. It is about the microwave sterilizations that affect the FFA content. So he's asking why the A, the sample A, which is not doing any microwave sterilizations, has high FFA, which is 20%. So is it if the FFA is 20%, drop to 5% after microwave sterilizations? So how can FFA to be reversed in this case? Yeah. So this is sample A.
Sample A is a palm fruit without any sterilization, raw palm fruit. So there we have not done any sterilization on the sample A here. So this is a raw one, palm fruit without any sterilization, no microwave irradiation, no conventional. So we just took the palm fruit and squeezed it, took out the oil, and we did the free fatty acid. And all these B, C, D, E are from microwave sterilization. We did microwave sterilization here.
Oh, so it's already a poor quality palm fruit.
This is a poor quality palm fruit.
Okay, explains that.
Yeah. This is a poor, really poor, lot of bruises, and we collected from the we collected from the ground, and from the trucks coming to the palm oil mill that has lot of loose palm fruits in the trucks, down there in the so we collected from there actually.
Yeah, thank you very much for your presentation, Dr. Asha. Is there any questions more for Dr. Asha? Okay. So yeah, I think the next speaker is not present. So we will have a coffee break now, and we will come back at this 3:30 p.m. Good afternoon, everyone. Welcome back to the sections of Waste to Wealth. So we will have our next speaker, which is Dr. Tena Pakiam from Institute of Materials Research and Engineering from this ASTAR UST Singapore. So Dr. Tena joined ASM under IMRE, which is the Institute of Material Research and Engineering in ASTAR Singapore from November 2021 as a junior research scientist. She is an alumni of the Monash University, Malaysia, where she undertook both bachelor's in biotechnologies and PhD in pharmaceutical formulations. Her strong interests revolve around of bio-based, biodegradable, recyclable, reshapeable and the green polymers. So she has filed a patent for novel formulations on semi-synthetic polymers from plant biomass as a pharmaceutical excipient in making vegetarian capsule. Dr. Tanner has over 10 publications and has been awarded over $200,000 in research grants and successfully supervised 4 master's students and 10 final year project students for the completions. The presentation's title is Biodegradable Thermo-Loaded Carboxyl Methyl Oil Palm Empty Fruit Bunches Cellulose Supported Polylactic Acid Bilayer Films for Active Food Packaging. The stage is yours, Dr. Tena. You may share the slide.
Thank you, Dr. Lee. Just give me a minute. Okay, good evening, everyone. So today I'm going to present about biodegradable thermo-loaded carboxymethyl oil palm empty fruit bunch cellulose with polylactic acid bilayer films for active food packaging. So basically what we have done is that we extracted cellulose from oil palm biomass waste. Now, why we use oil palm biomass waste? It's probably because Malaysia produced more than 300 million tons of palm oil on a large-scale plantation to meet the global demand. And therefore, it is widely used in retail food and snack manufacturing, personal care, biofuel, and many other applications as well. So hence, the dry palm oil fruit bunch waste fibers consists of 90% carbohydrate polymer, and this is actually going into waste. So basically, the idea of using biomass waste is for sustainability purpose, and we all know that cellulose fibers have the advantage of widespread availability, low cost, and high flexibility as well. So basically, it is abundant in resource, especially in Malaysia, and currently it is used in many fields, but most importantly, it has used as biomass fertilizer. These images basically show how oil palm fruit bunch looks like and the OPEFE. So in today's society, it is quite common to confuse the term biodegradable with compostable, leading to a major environment concern, which is plastic pollution. So the idea of actually utilizing biomass for plastic as a fossil fuel plastic alternative to replace it. Okay, this is basically because we want to reduce air, water, and land pollution, toxic to animals, and it affects the food chain, which is expensive to clean and recycle, plastic in general. So what type of cellulose have been extracted for this work? Basically, we extracted cellulose and we actually modify it to carboxymethyl cellulose. And why did we do that? It's because cellulose itself, it's hydrophobic, it's not soluble in water. So when we convert it to CMC, it's actually hydrophilic. It's linear, amorphous, long chain, anionic polysaccharide. So it can be used as a viscosity modifier or a thickener. Cellulose undergoes methylation to chemically change the sodium cellulose, and then it's carboxymethylated to CMC. The use of CMC in active packaging. So why do we actually use it? Is because we are trying to make a hydrogel from CMC and adding thymol into it. And why thymol? So thymol is actually a natural monoterpenoid phenol derived from thymine, which is actually present in thymine most of the time. It has strong antioxidant and antimicrobial properties. But the problem with thymol is that it has low aqueous solubility and low stability. So we are trying to use this incorporated with CMC to give it a better stability and and used in active packaging to stall microbial growth on food and also to prolong shelf life of food. So this schematic diagram basically shows how it actually works. We make CMC, we add it with thymol, and then we use aluminum chloride as a cross-linker, and we cast it in a mold. We also use PLA layer, has a bilayer on top of the CMC film. Okay, now the preparation of thymol-loaded CMC film is basically thymol is dissolved in 50 ml of 0.2 and NaOH, and then we add 150 ml of CMC solution that is dissolved in water. We sonicate for 150 seconds, and then we cast it on the mold. So the types of study we actually did was FTIR, rheological behavior, water contact angle, thermal behavior. We also did the biocompatibility study, antimicrobial activity, and the mechanical property as well. So basically, how did we actually extract cellulose from the palm oil fruit bunch? We initially washed and grounded the fibers, and then we bleached it using sodium chloride and acetic acid. Once it's bleached, we actually moisturized it with NaOH, about 17%, and then we washed it with acetic acid to neutralize it and with excess water. Once this is done, we then actually convert it to carboxymethyl cellulose. And basically the delignified cellulose is added into isopropanol and 25% of NaOH, and then stirred for 3 hours so that the cellulose would swell up. And then we added 3 grams of sodium monochlorate acetate, and that was stirred for another 2 hours. And then we extract it, we suspend it in methanol, and then we neutralize and dry the CMC. So that's how this end product looks like. So what we actually did was, after making the film, we decided to come up with several formulations of different percentage used. So this is actually the formulation code for various thymol concentration. So what we realized is that the thickness of the film we found for all the formulations were about the same. However, it was actually difficult to control because we were actually using a casting method. So the thickness varied a lot. So we had to do quite a number of formulations before we could actually narrow down to the best ones. However, what we found out was that after incorporating thymol into the film, it actually increased and improved the solubility and swelling property of the film. As the concentration increases, the swelling capacity increases, as you can see in the data here. And this could be because of the number of deprotonation of phenol groups increases in the film, causing to have a higher tendency to compete to form the ion crosslink with aluminium chloride, and therefore reducing the cross-linking between the cross-linker and the polysaccharide. This would also mean that it is also giving a lesser rigidity and increase the porosity of the network. So what we eventually did is that we did study the light transmission and the transparency of and the tensile strength as well. And what we realized was the tensile strength, as the thymol concentration increases, the tensile strength decrease. That's also the reason why it's because it is not that rigid. And this result shows the finding of thymol in FTIR. So what we realized that you could see an intensity increase in around 1,500. And this is probably because the cross-linking is actually taking place with CMC and aluminium chloride. And to see whether thymol is actually present, the group around 3,400 observed the thymol, the phenolic hydroxyl group, which indicates the thymol group in the film. So this actually literally demonstrates that thymol interaction with polymer through an intermolecular hydrogen bonds between thymol and phenolic hydroxyl group happen. So the next study we actually did was the weight loss study, the biodegradation study on the Flim, and also we did the we also took the the morphology study using an FE-SEM image. In the FE-SEM image, there was not much of a difference in terms of the different formulations of the Flim, but what we realized is that as we add thymol more, the Flim actually became much more smoother. In the biodegradation study, what we did is that we actually we actually added the Flim in the soil and we studied it over a period of 33 days. And we saw a reduction in the dry weight of the Flim. And it actually increased with the weight loss was higher as the concentration of thymol is higher. And that's probably because the matrix is not rigidly, the matrix is not that strong. So what we realized is that there is a significant increase in weight loss over time, ranging from 16 to 55%. However, you can see a minimal cross-linking degradation allowed for faster degradation. So we can see that when there is no cross-linking or no aluminium chloride is used, the example for the control, it degraded within 9 days. Whereas if a cross-linker is actually used, it takes up to 19 days to degrade. This is probably because of the hindrance effect of the chemical cross-link network on the enzymatic degradation. So the next thing in this image, I did mention the visual appearance of the Flim recovered at different composting time. And you can see that by day 33, most of the formulations have degraded completely. So we also did another study checking the microbial activity on thymol. And we saw that according to the image seen, it indicates an active agent penetrates through the Flim, forming a small zone of bacteria inhibition. It's not so visible, but you could actually see a very small zone of inhibition, and that is also probably because of the amount of thymol concentration used. So basically, this study is still ongoing. There's still much to do. But in conclusion, what I could say is that the extraction of CMC from oil palm biomass was actually successful. And the biodegradation Flim made from palm oil biomass can be augmented by adding active antimicrobial extract. And basically, in all these formulations, we decided that 20% thymol in CMC PLA showed the best mechanical strength and flexibility compared to the other composition. And it also have improved the inhibition bacteria zone as well compared to the control. So I would like to end my presentation here. Thank you very much.
Thank you very much, Dr. Tena. Any questions from the floor? I have one question here, Dr. Tena. Can you explain more about these applications for this active food packaging? Because you mentioned active food packaging, right? So what's the meanings about this and how it can be applied in this high-end food industry?
Yeah, so we were actually trying to do like a cling wrap method so that it is meant for actually for meat or cheese, you know, those kind of materials. This hydrogel packaging would work because when there is moisture, there is a tendency of the thymol to diffuse out and act on cheese, because we know that once you open a cheese packet, it will mold up really fast. So this is actually to prevent the molding, to take that to basically prolong the life shell of the Flim of the food. Sorry.
I see. So if let's say it's compared to the existing type of food packagings, right? So in terms of the cost of productions, it will be higher for your, I mean, your inventions.
Yes.
Or it
Okay.
will be like-
So because I have extracted CMC before using a different plant waste, and we have calculated the cost, and in fact, the synthesis of the CMC itself, we tried to use the most common reagents available and easy accessible. And most of the reagents used can be recycled as well. Like for example, methanol, you can actually distillate and use the methanol back. So we actually look into that. Yes, there might be a slight increase because the process method is a bit more longer than the one commercially out there, but we are looking into sustainability and we're looking into a long run usage. That's the whole idea here.
I think it's quite an interesting invention here. So hopefully you can, have more comparison study, so that it can convince the stakeholders about this interesting product.
I hope
Thank
so.
you very much.
All right, thank you.
Okay, so now we have our last speaker, which is Dr. Jahid Islam from Centers for Environmental System Biochemistry from University of Kentucky, USA. The presentation title is Effect of Carboxyl methyl cellulose molecular weight on the particle size of carboxyl methyl cellulose chitosan nanoparticles for drug delivery applications. So the floor is yours, Dr. Jahid.
Hello.
Yes.
Can you listen to me?
Yeah.
Okay,
I can hear you.
I'd like to share my screen now.
Okay.
Hi, this is Jahid. So I was a PhD student from Monash University, Malaysia under Dr. Pushpa. And now I'm doing postdoc in University of Kentucky. So my research was to prepare nanoparticle for cancer therapy, actually cancer targeting drug delivery vehicle. So what was made from carboxymethyl cellulose and chitosan nanoparticle. So I'd like to outline the nanoparticle formulation part for this presentation. So actually, maybe all you know what is cancer. This cancer actually humans' own cell, but it is abnormal, having abnormal growth because of the mutation. There is actually two types of cancer. One is benign that cannot spread. It is localized. There is another in which is most difficult to treat, that is malignant, because it can spread one place to another place throughout the body. So there is different approaches for cancer treatment, that is surgery, but if it is only successful when the cancer is localized. If it is spread, surgery actually not successful. There is another type of, that is chemotherapy. This is mostly used cancer treatment, but the chemotherapy has other disadvantages like adverse side effects, sometimes drug resistance. There are also radiotherapy and hormone therapy treatment, but they have also their own limitations. And so actually, maybe you can surprise why cancer treatment is so challenging. The most important thing is their cancer is not like single type. There are numerous type of cancer. Like in the same breast cancer, there is 100 type of breast cancer. So, and also cancer cell has unlimited growth. They can grow in many adverse conditions like hypoxia, low nutrient content or something like that. So still they can grow. And there is no specific target site. So we can target the cancer cell only. So if you want to target cancer cell, we also targeting the healthy cell. So there is very difficult to treat cancer without harming the human body. So for this reason, actually current chemotherapy has lots of limitation because it is highly toxic to healthy cells, and also there are poor biodistribution profile. Sometimes when we treat patient with chemotherapy, it actually goes to liver, heart, or kidney and damage this vital organ. And then there are also some chances of acquired cancer drug resistance. And as cancer has less developed lymphatic system, the drug absorption was also low. So there are some things we need to do to improve this limitation. So an ideal anti-cancer drug should be very effective, but it also have better biodistribution profile and better absorption profile. And it also should be stay in the cancer for prolonged period so that it can kill the cancer cell successfully. And after the killing, it should be excreted from the body without harming the body. So that's the main thing. So in this region, there are new approaches, that is encapsulating the anti-cancer drug with nanoparticles. So nanoparticle can bind to the therapeutics and then can retain, evade, and then directly target to the cancer cell. And after targeting, it can release from the body. And this is how we can actually improve the pharmacokinetics of the cancers of the anti-cancer drug. So maybe you can think how this cancer targeting actually works. So if you see the blood vessel of cancer cell here and blood vessel of healthy cell, you can see the cancer cell has loosely bound blood vessel cell. These are epithelial cells. So as these are loosely bound, so if we can design some nanoparticle that can pass through this loosely bound, but it cannot pass through this tightly bound healthy cell. So the nanoparticle will carry the drug to the cancer cell only, not the healthy cell. It cannot pass through here, so it will not go to the healthy organ, but it can, as it can pass through here, so it will go to the cancer cell, and thus it will kill the cancer cell directly. It will not harm the healthy body. So this is known as a passive targeting, and also there is this effect is known as EPR effect, that is enhanced permeability and retention effect. So there are also another type of targeting that is known as active targeting. In that case, we can bind the nanoparticle with different kind of receptor. That receptor actually will bind to the cancer cell specifically. It will not bind on the healthy cell. It will bind. It will have more affinity to binding with the cancer cell. So it will go. It will accumulate in the cancer cell more compared to the healthy cell. This is how we'll target cancer cell. That is, one is passive targeting, other is active targeting. So in this passive targeting, particle size is very important. So we'll look into that. So how to optimize the particle size so that we can make a very good quality nanoparticle for cancer targeting drug delivery. So there are many kinds of nanoparticles that are used. That is polymeric micelle, dendrimers, liposomes, viral nanoparticles. This all nanoparticle has their own merits and also demerits. So we are working with polymeric nanoparticles because of diversity and ease of application. So these are the limitation of current nanoparticles. The major limitation is the nanoparticle has some chance of immunogenicity. So also the nanoparticle has different binding sites. So body protein can bind to the nanoparticle and then can alter their mechanism and their reaction with the body. And sometimes a nanoparticle digest very quickly by the body enzyme. So this EPR effect actually cannot work. So there should be more cancer targeting strategies like incorporating some binding ligands to the nanoparticle. And also there are some nanoparticles, basically lipid based nanoparticles like liposomes and something like that. So they have very slow drug release, and also there's in that case the bioavailability is very low. So the some nanoparticles also are very low for stability, and also they have less bioacceptability, and there are also poor repeatability, poor scalability, because the nanotechnology system is very sensitive. So repeatability and scalability is very challenging. So this is our proposed drug carrier formulation. This formulation actually concerned about the limitation. So we're trying to develop a nanoparticle which will not have this limitation. So this nanoparticle will have multiple drugs inside the nanoparticle core. It can be bound, it can be entrapped in the nanoparticle, and then there will be both organic and inorganic building blocks. So we'll have advantage of both organic and inorganic system, and also there will have some targeting ligands these ligands will bind to the cancer cell. It will not prefer to bind healthy cell, it will prefer to bind cancer cells. So there will be both active targeting and also passive targeting. So by the means of these two different kinds of targeting, it will prefer to go to the cancerous site rather than the healthy site. So it will have very less side effect compared to the free drug alone. I mean the current strategies of treating cancer. And so as I said, so from the previous slide, we can find that if the nanoparticle size is higher, then it will have more chance to go to the cancer site rather than the healthy site. But there is a problem. So if particle size is higher, there is higher chance of that immune system will recognize as a foreign particle and then be knocked out by the immune system. So we cannot make very little, and we cannot make it very large. So there is a very narrow gap. Like this gap is around 200 nanometer. So if the particle size is around 200 nanometer, then it will work a good nanoparticle for cancer targeting drug delivery. If it's less than that, say less than 100 nanometer, it will not work good, but because in that case, it will go to the healthy organs as well, like kidney, liver, or lung, or brain. So if we make it like large, like 500 nanometer, in that case, it will be knocked out by our immune system. So there is a very narrow gap. So we have to prepare nanoparticle such a way that the particle size should be stay around 200 nanometer. So we prepare the nanoparticle use CMC and chitosan, and also hybridized with calcium carbonate. And we optimized the concentration and the type of CMC so that the particle size is around 200 nanometer. So here is the preliminary result. So we prepared the CMC and chitosan nanoparticle, and we found that there is a diverse pattern of particle size. So it is not homogeneous, it is heterogeneous nanoparticle. It was so actually we found that from this result there is a some modification is required in chitosan and carboxymethyl cellulose. So we use microwave reactor. As we know, the particle size has the molecular weight has a great impact on the particle size. So we used microwave-based degradation of carboxymethyl cellulose so that we can modify the molecular weight of carboxymethyl cellulose to prepare the suitable nanoparticle with suitable particle size. So this is the modification system. So we use 150 degrees Celsius for 15 minutes, 30 minutes, 45 minutes, and 60 minutes to prepare different kind of CMC, and then we calculate the viscosity, and from the viscosity we calculate the molecular weight of the CMC. So you know, so it was initially the molecular weight was 250 kilodalton, and then after 30 minutes of carboxymethyl cellulose, 30 minutes of microwave reaction, the molecular weight reduced to around 40 kilodalton. Based on this formulation, like ratio and degree of polymerization of CMC and concentration of hydrogen CMC, actually we optimized the particle size. So here is the result. So if you see CMC content based on molecular particle size actually increase based on the CMC content. If the CMC content increase, the particle size increase. It is around 50, in 70% CMC content, it was around 1500 nanometer. So, and then we used different degraded CMC, that is CMC3, CMC4, and CMC5. We found that after using degraded CMC, the particle size actually decreased. But still the particle size is above 100 nanometers. So then we use different strategies. So to reduce the concentration of the carboxymethyl cellulose and hydrogen. So here is 1 milligram per ml, and then we reduce to 500 microgram per ml to 200 microgram per ml. So after using 200 microgram per ml, we found the nanoparticle size was around 180, and with the there is very little effect of hybridization on the particle size. So this CMC3 actually has the more suitable for the optimum particle size, because it is still comparatively large. It has comparatively large molecular weight, but still in the range. So if the molecular weight is large, then the stability will be better. So we prefer to keep the molecular weight large, but still it should be in the range. So from CMC4 and CMC5, we prefer CMC3. And so after that, we prepared the conjugated nanoparticle, that is conjugation by a targeting ligand, that is folic acid. And then we also optimized the particle size. After we saw the particle size was increased with folic acid content, but then we fixed it with mixing the folic acid and conjugated hydrogen and free hydrogen, and then we prepared a nanoparticle that has proper particle size and also a active targeting system. So this is the final. Final formulation. This final formulation have around 160 nanometer particle size, and it has active binding and passive binding strategies. So here is my conclusion. So we found that 7:3 hydrogen CMC and 200 microgram concentration have the most suitable particle size, and CMC that is degraded in microreactor and 200 microgram per ml concentration is the most promising. So we use this ratio for further formulation and characterization. Here is my reference. Thank you.
Thank you very much, Dr. Jahid. Any questions from the floor? Before that, I have one question, Dr. Jahid. So how do you determine the molecular weights of these CNCs and degraded CMCs?
This molecular weight is based on the rheological study and the intrinsic viscosity, because from this intrinsic viscosity, so we know the viscosity and molecular weight of the commercial one. So from this, there is a linear relationship between the viscosity and the molecular weight. So it is known here, molecular weight and viscosity both. And here we know the viscosity, but not the molecular weight. From this, we can calculate this.
So it is from the data of viscosity, then
yes,
it can be used to determine the molecular weights. Okay. So do you perform any morphological analysis to confirm whether the size of original CMCs have been smaller?
We did APSCM, we did ACM, and we also did TEM to confirm visually. So I haven't presented it here, but we had the data.
I see, I see. Okay, okay, thank you very much. So if don't have any more questions, then I'll say thank you to very much for your presentations, Dr. Jahid. So because you are purposely joining these webinars at this early mornings, right, from this Kentucky, okay. So yeah, we are very appreciate for your, these participants in these presentations. So you can have your good rest.
Okay, thank you, thank you.
Okay, yeah. So ladies and gentlemen, we are reached at the end of these sessions, Waste to Wealth. And thank you very much for all the participants. And we will see you all again tomorrow. Okay, thank you very much and have a good day ahead. Bye-bye.